Hello everyone, welcome back. Let us continue our discussion on reinforced concrete design. We are in week 2 and this is our 6th lecture. So we have learned how to design against flexure, and if we have singly reinforced and doubly reinforced beam, we have learned how to calculate the moment of resistance. We have also learned how to deal with flange sections. Today our main aim of this discussion is to design against shear. Now for that, let us first consider a simply supported beam. As you can see, now this beam is loaded with a UDL, and due to this reason we will have shear force acting at every section in addition to the bending moment, right? Now at the section level we can evaluate the shear stress distribution, as you can see here. So this is the shear stress distribution at the section level, and that shear stress distribution is governed by this expression, which is effectively tau is equal to VQ by IB. Obviously at the topmost fiber and the bottommost fiber tau is 0. And then as we go deeper at the middle, we have maximum value of tau here. That comes from this expression of tau, as you can see. Now at y equal to 0, tau is equal to 1.5 times V by BD. V is what? V is the shear force. So this is the shear force at that particular section. So this shear force divided by BD, which is the area, is basically the shear stress, and if we increase it by 50%, we get this tau at y equal to 0. So y equal to 0 means at the neutral axis. That means tau maximum is equal to 1.5 V by BD, right? So this is the maximum value of tau. Now let us see the shear stress variation over the rectangular section. So if we have a neutral axis, as you can see here, so it starts from 0, then it increases and reaches up to this point, and beyond this point below neutral axis, because we have ineffective concrete, the entire shear force is actually taken by this steel, and that's the reason it is rectangular up to the level of tensile reinforcement, right? So that's the variation. Now our task is to design against this shear stress acting at a particular section. Now the question is, why these type of shear reinforcements are provided? For that, let us just quickly see pure bending case. As you can see, in this case we have this PP loading at the quarter points. Then for that we have this region which is under pure bending. Now if you look at the cracks, obviously if you take a small section here, it is under axial tension, as you can see here, and therefore tensile cracks appear. Now if we shift our attention to the ends, obviously for this load at the center we have maximum bending moment at the middle, while maximum shear force at the ends. Therefore if we take a small element and then draw the stresses, we have, this is the situation. The bending stress is almost equal to 0. It is actually 0 at the end because of free hinge support. So now for this type of stress block, we have this diagonal where we have the shear cracks. So effectively what we have at the middle, we have these vertical cracks, but as we go towards the end, we have this diagonal cracks. The question is how to prevent this diagonal cracks with the help of these T-ups. And for that, again, let us consider a part of this beam. As you can see here, there is a photograph of shear reinforcement provided. So these are the longitudinal reinforcement and these are the shear reinforcement, right? Now total shear resistance of this particular section, say we are somewhere here. At this section, total shear reinforcement is given by this expression, where Vc is the shear resistance of the uncracked concrete. Then VAY is, as you can see here, this VA. At this crack level, we have aggregates. Then they offer a resistance against a resistive force which has a vertical component that acts in the plane of shear. So VAY is the component of resistance offered by the aggregate interlocking, because we have coarse aggregates and fine aggregates there. Then VD is the longitudinal bars providing some resistance due to dowel action, and that is shown here. So we have VC, we have VD, we have VAY, and then we have VS. This VS is actually the shear resistance provided by these stirrups. Now, if you look at the cross sections, we have longitudinal bars here, and then at the top we have longitudinal bars. Then we have stirrups going all the way, and that actually provides this rectangular geometry. So it holds this longitudinal bar, and at the same time, if we take a cross section here, it provides some shear resistance, and that is shown by Vs. Now, Indian Standard Code IS 456 provides tau C, that is the design shear strength of concrete. So if you select a grade of concrete and the percentage of longitudinal reinforcement, which is here, longitudinal reinforcement, then from this table 19, you can find out what is the value of tau C. Now, the shear resistance of section without shear reinforcement is actually tau C times BD. So tau C we get from this table 19. For that particular section, we know what is B and D, so we can calculate this tau C times BD, which is actually balancing these three forces. Now, if we have a requirement more than that at a particular section, then obviously we have to design this VS, and that's the main theme of this discussion, how we can actually design that. But before we go into that details, let us first quickly go through the code clause that actually tells us the location of critical section for which we actually design these shear reinforcements. As we have already seen, for a simply supported beam, as we go towards this region, we have shear force more dominant than bending moments, right? So clause number 22.6.2 actually defines the critical section. So if we have a beam which is supported over, say, a pad, like as you can see here, it will develop reaction at the center, but from the face of this bearing at a distance d, which is the depth of this beam, is the location of the critical section. So we first need to identify this critical section, and then at that section we have to find out what is the shear force, and then we have to take a decision what should be the minimum shear reinforcement or the exact shear reinforcement that we need to provide. Now, if the configuration of beam column changes, then the location of the critical section also changes. For example, here in this case of corbel, the critical section is here. So the first task is to identify the critical section, and then once we identify the critical section, our task is to design the shear reinforcement at that particular section. Now for that, let us first discuss the nominal shear stress as per IS 456. So it considers uniform shear stress distribution. So if we have a rectangular cross section, then over this cross section, instead of parabolic, it considers a uniform cross section. So that is tau V. So this nominal shear stress is nothing but the applied shear force with appropriate factor. Just like in case of bending moment, we evaluated BMU. In case of shear force, we calculate VU with appropriate load factors for different load combinations. Then that divided by B times D is the nominal shear stress, which is rectangular throughout the section. Now, in case of beam with varying depth, how do we evaluate that? Let us consider this cross section as you can see here. So, in this case, we have bending moment and depth are increasing in the same direction. So, as we go this way, both of them is increasing. So, in that case, what we do, we first find out what is the applied bending moment and then the resistance of the section. And if we balance these two, we actually get the amount of tension. If you recall, at that particular section, we know what is the bending moment. Now, because this is a varying section, it's still the reinforcement is inclined, which is parallel to the bottom surface. So, if we take a section here, this T is the tensile force. Now, to find out the sectional capacity, we have to find out first this component which is in horizontal direction, and that multiplied by the lever arm will give us actually the capacity that we have to balance with mu. Now, using this expression, we can find out what is T, and then it is mu by d cos beta. Now, we use this approximation for the time being, but of course, for a beam section, we can go for an exact lever arm. But for the time being, let us consider this is the lever arm and let us see what happens. Then, at the y direction, that is the vertical direction, we have the force balance equation as you can see. So, we have this omega L by 2 as the reaction minus this is the force over a section of x, and then V is the shear force acting at that particular section minus the component of this T in the vertical direction, that is T sin beta. So, what we can do, we can evaluate the shear force acting at that particular section, and then we can find out the nominal shear stress using this rectangular distribution over the intersection. So, first we find out this Vu, then that Vu is effectively modified with this component of the force coming from the rebar, and then that divided by the BD. Now, if we have a reverse situation where bending moment and depth are increasing in the opposite direction, then obviously if we follow the same procedure, what we'll have is actually a positive sign. All other derivations will remain same. So, we can find out what is tau V. That is the nominal shear stress. Obviously, the direction of the forces are important. We have to keep track of proper dimensions and the sign conventions. Now, in case of shear design, what are the steps? First, in step 1, we again calculate what is the factored shear force acting at a particular section, which is the critical section. Then second, we calculate what is the nominal shear stress using this expression. Plus or minus will be governed by the case that we deal with, as we have already explained. Now, this tau V must be less than equal to tau C max. The tau C max is the maximum shear stress capacity of section without shear reinforcement. This is very important. So, from IS 456 table 20, we can evaluate this tau C max, which is 0.63 times square root of FCK. So, it actually depends on the grade of the concrete. Depending upon the grade, we can evaluate tau C max. So, if tau V is greater than tau C max, then we redesign the section. Now, in the next step, what we do? We calculate tau C. How do you calculate tau C? It is from table 9 of IS 456, and it depends upon the grade of concrete and the percentage steel. With the help of these two, we can actually calculate tau C max. Now, this percentage steel is what? It is the longitudinal steel. So, if we have, this is the cross section and the longitudinal steel are given here, we can find out what is PT, and we know the grade of concrete here. Based on these two information, we can calculate tau C. Now, for different cases, there is a modification of this tau c. For example, if we have a section where we have axial compression, then this tau c is modified with a factor delta. Delta is the minimum of these two, which is as per clause number 40.2.1.2. In case of a slab, depending upon the slab thickness, we have a modification factor K, and if we multiply K with the tau c that we have already evaluated from this table 19, we get the actual tau c for this slab. And that comes from this clause 40.2.1.1, and depending upon the depth of this slab, overall depth in millimeter, we need to identify K, and that K we multiply with tau c to get actual tau c that we use for design of shear reinforcement in case of a slab. Then the next step is, if tau v is less than tau c by 2, then nominal shear stirrup can be provided in primary members, and no shear stirrup is provided in members of minor importance, for example lintel. So for the time being, let us not focus on this. So if this condition is satisfied, then we provide nominal shear stirrup that I will explain in a minute. For nominal shear stirrup, we have a dedicated clause which is 26.5.1.6, and here it tells ASV is the area of or the cross section of the shear reinforcement. Now if we have a rectangular cross section, at a particular section we have, this is the shear reinforcement. So we have two legs here, and then depending upon the phi of this, we can calculate the area, multiply it by 2, that will give us the total cross section. We'll see that in a minute. Then along the length of the beam, this shear reinforcement will have a spacing that is given by this SV. So we can evaluate ASV if we fix the spacing from this formula, or otherwise we can evaluate the spacing if we fix the ASV. Either one, either we fix SV and then find out ASV, or we fix ASV then find out SV. Now here B is the width of the beam and Fy is the characteristic strength of the shear stirrup. Now there is a limiting clause that we can actually go up to maximum of 415 for this Fy value in case of shear reinforced design. Now, as I said, we can have a minimum of two-legged stirrup. Sometimes we have multiple legged stirrup, like in this case we have four-legged. So if we have two-legged stirrup, we calculate the cross-sectional area of one reinforcement, multiply that by 2 and we get ASV. Now if we have four-legged, obviously we have to multiply it by 4. Now if there is a situation that the tau v that we evaluate is in between tau c and half of tau c, then we provide this nominal shear stirrup, and if tau v is in between tau c max and tau c, then we design shear reinforcement. Now what is the shear force for which we have to design the shear reinforcement? We have tau v that we have already calculated from Vu, and for the cross section without reinforcement we have tau c. So the difference between these two times Bd is basically the force for which we need to design the stirrups. Now we can also provide inclined stirrup, as you can see here. In case of inclined stirrup, this is the expression as per the respective codal clause, as you can see here. So if the alpha is the angle with horizontal, then VUS is given by this expression. So we can provide now the shear reinforcement once we calculate and check the value of tau b if it is in between tau c and tau c max. Now in addition to this inclined stirrup, a different situation also arises. For example, if we have continuous beam, say, then the bending moment diagram and for this type of beam is something like this. So we have a hogging moment here at the support and sagging moment at the middle. So if we see the main reinforcement, obviously at the middle we have these bars, while when we go over the support, we have the main reinforcement at the top, because due to hogging bending moment, we have tension at the top, compression at the bottom. Now to have these type of reinforcement arrangement, what we can do, we can have a bend up bars. So the bars which are at the bottom, some of the bars can be bent up and brought to this top surface, and that's why we have this kind of situation. Now if that is the case, then this bent up bars also provide some resistance against shear. Otherwise, in a normal case, we have this type of vertical stirrups that provide shear reinforcement, and which we can actually find out from this expression. So our task is to find out this VUS, as I have already explained. Then you select this SV. If you use this expression, you can find out what is ASV. Now in case of bend up bars, this steel rebars also provide some resistance against shear, and that is given by this expression. But the code says that not more than 50% of the shear force taken by the shear reinforcement, that is this quantity, is assumed to be taken up by bent up bars. So that limitation is there. I'll explain that with some numbers in a minute. But remember, even if we have a higher capacity, we can not go to that full capacity. We have a limitations of 50%. Now these bent up bars are always provided with shear stirrups. So shear stirrups are designed for maximum of the following forces. So these are the two cases. So in the second case where we have bent up bars, I have already explained. So this is basically the shear force, and then this is the capacity of the bent up bars, right? Now let us put some numbers. So if we have VU, say 200 kilonewton, VC 30 kilonewton, and then shear force taken up by the shear reinforcement is the difference between these two, that is 170. Now if we have bend up bars, say in one situation we have its capacity against shear is 250, and in other case it is 40. Then in the first case, we can go up to half of this value, which is here, that is 85 kilonewton from these bent up bars. And then for the other case, because we have a smaller value, in that case, we can go for the shear force for the stirrup as 130 kilonewton, which is the difference between this value here minus the capacity offered by the bent up bars. Now, lastly, there is a maximum permissible spacing of stirrup. SV is the stirrup spacing. So if we have, this is the beam, and if these are the stirrups, so this is the spacing of the stirrup, SV, which is here. So there is a limitation of this SV. So first we calculate SV as per step 5, that is the previous step. Then using this expression as per code clause mentioned here, then there is a limit of 0.75 D and D for vertical or inclined stirrup, and then finally 300 millimeter. So minimum of these 4 possibilities we have to provide as the spacing of the stirrup, right? So it means that the maximum spacing of the stirrup is 300 millimeter. We cannot go beyond that. Okay. Now let us take an example. So we have to design this 4-legged vertical stirrup for VU, which is given 1000 kilonewton. So the shear force we know at that particular section, which is the factored shear force at the critical section. Then first what we find out is the nominal shear stress, that is tau v. It is coming from this expression. Now in our case we have no bent up bars or varying cross sections, so this beta is equal to 0. Effectively we have tau v, which is Vu by Vd. That you can calculate because Vu is the 1000 kilonewton and then the size of the beam is 500 by 1500. Now capital D is 1500 and then the effective cover is 100. So we have small d is 1400. So tau v in our case is 1.43 Newton per millimeter square. Now this RC section has M30 concrete and Fe 500 bars. So for this concrete, M30 concrete, from table 20 what we get, tau C max is 3.5 Newton per millimeter square. So our tau v is less than this tau C max. If it is more than tau C max, then we have to redesign the complete section again. Now our next task is to find out tau C. For that, what we have to do, find out what is the amount of longitudinal steel provided. So in our case, we have 21, then 25 by bars. So that is here. And we can calculate percentage steel, which is 1.47%. And for this percentage steel and M30 concrete from table 19, we can get the tau C value is 0.75 Newton per millimeter square. So what we see, we have tau v, we have tau C max, and then we have tau C. Then in our case, we have our tau v, which is in between tau C max and tau C, as you can see here. It is 1.43, which is less than 3.5. but more than 0.75, right? So then what we have to do, we have to design the shear reinforcement, and for that what we do, we subtract tau C from tau v, because tau C is already provided by the cross section without reinforcement. So the difference times Bd is the Vus that will be taken care by the shear reinforcement, which are actually these stirrups. So Vus we figure out is 476 kilonewton, right? Then let us design with 8 phi bar, as you can see, and we have 4 legs, 1, 2, 3, 4. So we have 4-legged 8 phi bar, and then what we do, we can calculate ASV because we have already selected this 4-legged 8 phi bar. And that you can see here. So we know ASV, we know Fy. Just recall the steel category here. It is Fe 500, which is more than 415. But here we have that limiting value of 415, which we use here. Then the only unknown is SV, and SV is 213.5 millimeter. So now we have to find out the minimum requirement, and for that we have 4 options. The first one is obviously 213.5. Then second one, based on this expression, we have to find out the spacing, and that spacing is 362.96 millimeter. Then in this problem we have to go for 0.7D. So 0.7 times 1400 is 1050, and then ultimately the last one is the 300 millimeter. So minimum of all this is what we have found out, and that is 213.5. Obviously we cannot provide this, so any dimension less than this is okay. Normally at the construction site, it is in terms of in integer multiple of 25 millimeter, that is roughly 1 inch. So what we provide is 200 millimeter center to center of these stirrups, which are 4-legged 8 phi bars. So that satisfies the design. And what we see here is the step-by-step procedure how we design these shear stirrups. And obviously, we'll see as we go along the beam, the shear force varies along the cross-section of the beam. We have designed this at the critical section, but for example, if you have a simply supported beam, at the middle, we'll have a region where we have a low value of shear force, and there we can provide different stirrup spacing according to the need. So normally along the length of the beam, this shear stirrup spacing varies, and we need to design that along the length of the beam. Let us take a different example. In this case, we have to design the shear reinforcement for this working shear force of 200 kilonewton. We assume 2 bars as bent up bars, as you can see here, and the diameter of those bent up bars are also given. So the cross section is given, B is equal to 300, D is equal to 600, and it is made of M20 and Fe 500 bars. And this alpha is equal to 45 degree. So the step 1, we first find out VU. We have to multiply this with the appropriate factor, and in this case it is 1.5. So we have the design value of ultimate shear force is 300 kilonewton. Next step, we find out what is the nominal value of the shear stress, that is tau V, which is equal to VU by BD. Now what we have here is 300 into 10 to the power 3 divided by BD, and then ultimately what we get 1.67 Newton per millimeter square. Now for the grade of concrete of M20, tau C max is 2.8. So tau V is less than tau C max. Next step is, let us find out tau C. For that we need to calculate PT, percentage of steel, and here the percentage of steel is actually 0.35. Now for PT equal to 0.35% and M20, from table 19, we can get this tau C is 0.39 Newton per millimeter square. So what we see, our applied shear stress tau V is in between tau C and tau C max. So if that is the case, we first have to find out what is VUS, and that is 230.4 kilonewton. Then next we have to find out the capacity of the bent up bars. For that, I have already explained this earlier. Alpha is 45 degrees, so we can find out what is the capacity, which is 160.41. Now, even if we have bent up bars, we always provide bent up bars with shear stirrups. So shear stirrups are designed for maximum of the following shear forces, right? So we have, these are the two cases, and maximum of that we actually take. So we have this value tau V minus tau C multiplied by BD by 2, that gives 115.2 kilonewton, and then we have this as Vs minus the capacity of the bent up bars. What you see here, effectively it is 66.99 kilonewton. So then what we do, we design the shear stirrup spacing. For that again we have assumed it is two-legged 8 phi bars, and then we have already calculated VUS maximum of these two, as I said, which is 115.2 kilonewton. So that is equal to 0.87 Fy ASVD divided by SV. Now again we have used Fe 500 bars, but because of the limitations we have to use 415 here as the value of Fy when we design shear stirrups. Then from this expression we can find out what is SV, and that is 189.04 millimeter. Then finally what we have to do, we have to check the maximum permissible spacing of the stirrup. So the first one is 189.04. Then using this expression we find out the shear spacing, which is 302.4. Then for this problem it is 0.75D, which is 450 millimeter, and finally 300 millimeter is the limit that is the fourth option. So minimum of these four options is 189.04 millimeter. So as I said, we provide in multiples of 25. So the lower value of 189.04 millimeter is 175 millimeter. So we provide two-legged 8-5 bar at the rate of 175 millimeter center to center. So that actually completes the design. Now let us take a different example. In this case, as you can see, we have to design this shear reinforcement. For the section, we assume two 32-5 bars are curtailed before critical section. So this is the critical section. We have longitudinal bars here, and sometimes it is bent up, sometimes it is curtailed. So some of the bars are curtailed, as you can see. So in the tension zone, what we have here is 4 32-5 plus 1 16-5. And again, it is made of M30 concrete and Fe 500 steel. Now, out of these combination, as we go to the critical section, we have curtailed two 32-5 bars. So that means we have two 32-5 plus 1 16-5. And then for this problem, we are given this UDL, and the effective length here is 11.45 millimeter. Then at the critical section, we can find out the value of shear force, which is 276.64 kilonewton. Then we have to design against this value. First, what we do, we find out the value of tau v. In this problem, we have tau v as 0.85 Newton per millimeter square. First, we have to check whether it is less than tau c max. So for M30 concrete, as per table 20, tau c max is 3.5. So tau v is less than tau c max. We don't need to redesign the cross section. Then next, what we check is tau c. For that, we find out what is PT, and then percentage steel we evaluate 0.56%, and then we find out what is tau c. And then from table 19, it is 0.52 Newton per millimeter square. So effectively, VUS is 105.6 kilonewton. Then we have assumed two-legged 10-5 bars here as the shear reinforcement. Now we can balance this VUS with the help of the shear reinforcement that we provide. So we know ASV, we can calculate ASV. Finally, we have to check the different options. So the first one is 429.6 millimeter that we get from previous step. Then from this expression, we get the shear spacing is 354.46, 0.75D, which is 600 millimeter, and then 300 millimeter. Of all four possibilities, the minimum one we have to provide. So the minimum value here in this case, as you can see, is 300. So we provide two-legged 10-5 bar at the rate 300 millimeter center to center. Now, it clearly shows how we design the shear reinforcement based on the shear force at the critical section. So just go through these steps, all these expressions, code clauses, and if you have any doubt, do let us know, and then we will clear your doubt. Otherwise, we will continue in our next class on the other topic of design of beams. Thank you very much.